Okay, in this presentation we're going to look at the Pareto distribution. I'm going to do something very interesting. In particular, we're looking at the type 2 distribution, which is also known as the Lomax distribution. The two-parameter Pareto distribution, type 2 Lomax, has the following survival function. Okay, S of x equals theta divided by x plus theta all to the power of alpha. Okay, so that's alpha up there, power of alpha, where x is greater than 0. Derive the mean of the Pareto distribution using the Pareto distribution, type 2 distribution, using the survival function approach. Okay, what is the assumption? What assumption is made on the shape parameter alpha? Okay, so this is the mean. Okay, this is just notes I have, so it just gives us a bearing. Okay, so this is the type of knowledge we would need, and in particular this part here. Now, so alpha and lambda are assumed to be greater than 0 just to begin with. Okay, but for this to be a positive number, okay, that means additionally alpha has to be greater than 1. Okay, if it's not, the mean is undefined. Okay, if it's less than 1, the mean is undefined. Okay, that's what assumption is made on the shape parameter alpha. Okay, so that's really it. Okay, so anyway, let's begin. This is the survival function here, and it's essentially, the survival function is the complement of the cumulative distribution function. Okay, and this is the formula you would use to calculate it there. The expected value of t is the integral from 0 to infinity of s of t, the survival function, denominated in terms of the variable t, dt. Okay, so let's just begin there. The expected value of x is that integral there. Theta divided by x plus theta to the power of alpha dx. Okay, so what we can do there is rearrange that, make it two expressions. Theta to the power of alpha times x plus t to the power of 1 minus alpha. Okay, dx. Okay, now so there's a big chunk that essentially, first off, theta to the power of alpha, that gets taken out. Okay, and when we differentiate that, when we integrate that, we get x plus theta to the power of minus alpha plus 1 divided by minus alpha plus 1. Okay, it's a very straightforward integration. Okay, power rule. And what we're going to do is integrate or evaluate them at infinity and 0. Okay, so this part we can just take out altogether. That there's no expression there in terms of x, and what we're left with is this part here, 1 over x plus theta to the power of alpha minus 1. Okay, so essentially just invert it and change the sign. When we evaluate that at infinity, we have 1 over infinity. Okay, infinity plus theta is infinity, so we just assume that is equal to 0. Okay, and then we have, when we evaluate it at 0, we have 1 over 0 plus theta to the power of alpha minus 1. Okay, and that is that expression there, and you can see this is sort of starting to progress very quickly. We have a minus sign there and a minus sign there. That becomes a plus. The minus signs just go out of it. So on the numerator we have theta to the power of alpha, and on the denominator over here we have theta to the power of alpha minus 1. So when we divide them out, we end up with theta divided by alpha minus 1, and that's essentially what we're asked to do. Okay, and in order for this integral to converge, we assume that alpha is greater than 1, but essentially there's multiple ways we can explain it there. I've done it already, so we can leave it there. Okay. So just actually the shape parameter has to be, you can sort of immediately state that the shape parameter and scale parameter have to be greater than 0. So we already know that theta is going to be greater than 0. So for this to be a positive number, because the support of the distribution function is 0 to infinity, this has to be a positive number. And the only way that makes sense is if alpha minus 1 is greater than 0, which say alpha is greater than 1. Okay.